Okay, is my audio coming through now, Chris?
Can hear me. Let me just verify here.
I can hear you. Can you hear me?
Okay, perfect. Thanks, Mike. We will go ahead and get started. So thank you all for coming out to my talk. As the title says, today we'll be taking a glance at interpreted language bytecode trickery. My name is Chris Lyne. I'm a senior researcher at Tenable on the zero-day research team. And the team's goal is to find unknown vulnerabilities in third-party products. We also coordinate disclosure with product vendors when we find vulnerabilities. And just like we're doing today, we also share our research with the community. Some background for this talk. There were two research projects that kind of sparked the content for this. I was looking at Druva inSync, which is an endpoint backup software. And I was looking at Nagios XI, which is an enterprise server and network monitoring software. And like you see, Druva was written in Python, Nagios is written in PHP. So the idea initially is to get your eyes on the source code and try to make sense of how the product works, under the hood. Hopefully, we can understand it well enough to find some vulnerabilities in it. The problem was both of these products had implemented some form of code protection. So I wasn't able to read the source code. So some topics we'll cover today are interpreted languages, PHP and Python. We'll look at bytecode. We'll also look at some bytecode protections and also how I went about bypassing them to understand application logic. So first we'll talk about compiled versus interpreted languages. So as you see on the left here, some examples of compiled languages are C or C++ or Go. Basically, a compiled language requires the programmer to explicitly compile that source code into an executable format, which is, it's machine code. It runs on the operating system, which runs on the processor architecture, right? Today, we'll be talking about interpreted languages, which are a little different. The programmer doesn't have to explicitly compile the source code. However, there is an interpreter program that will interpret the source code, convert it into bytecode format, which can then be executed by a virtual machine. So for instance, like the Python virtual machine will execute Python bytecode. So first we'll talk about the Python opcode remapping, which I saw in Druva inSync. When I first started researching Druva, I realized that it was built with Py2exe. So what led me to believe this is, if you look at the procmon output at the top here, you can see that when the inSync exe process launches, it loads up a Python 2.7 DLL, and it also loads up a library.zip. If you were to look in the library.zip, you would see a bunch of PYC files. And these are all Python modules. This behavior is indicative of Py2exe. And what Py2exe does is it allows the Python application developer to distribute the final product as a Windows executable. So there's a Python interpreter that's delivered with it along with all of the required modules. So you might be asking, what is a PYC file? Well, it's a byte compiled Python file. And a lot of times modules are converted into that byte compiled format in order to help speed up the load time. So when you go to import a bunch of modules into your code, it loads faster. It's already compiled. However, if you were to try to open up that PYC in a text editor, you wouldn't be reading source code like you would in a regular Python source file. It's a binary format. So in order to get that Python source code back, you would have to use a decompiler such as uncompile6. So in the screenshot here below, you can see I took the Python struct module and ran it through uncompile 6 and decompiled that PYC file back into source code. And it's pretty simple. There are just 3 imports. So the protection I encountered was that I wasn't able to decompile the Druva inSync modules that were delivered with it. And when I tried to run uncompile 6 on the struct module that was packaged with Druva, I got an interesting error. It said unknown magic number 62216 in the file. So I figured there was something funky about the file. And so that led me to dig deeper into that PYC file format. In order to dig into it, I started with a hello world. The Python script was just, it's just one print statement. I used the PyCompile module to create a PYC from that source file. And below you'll see a hex dump of the resulting PYC file. First 4 bytes are what's called the magic string. The second 4 bytes are the timestamp of when the file was created. And then the remainder of the bytes are a code object. We'll talk a little bit more about magic string and code object. So as you just saw the magic string contains a number in it called the magic number. And that represents which Python version compiled it. So we saw that the 62216 was an unknown magic number. If you were to look in this list, which is a documented list of magic numbers, you don't see 62216. So that kind of explains why the decompiler didn't know what to do with the file. But if you notice, there's a 62211, 62201, 62291. These are all magic numbers that line up with Python 2.7a0. And each magic number is a new revision. So as you can see, with this magic number, it introduced setup with, it introduces build set, map add, set add. These are all new instruction types being added. So these instructions all map up to a specific opcode. For instance, on the highlighted line here, you can see that the call function instruction maps up to opcode 131. And then so on. There are plenty of more instructions. Make function 132, build slice 133. So there's a module in Python called the Opcode module. And if you were to dump the Opcode map using that module, this is the output you would see for a normal Python 2.7 installation. I want you to take note of where the arrow is pointing. So the call function instruction has an opcode of 131. And also keep in mind here, duptop is a 4. So we'll just look at those 2 for now. But if we were to look at the Druva opcode map, you would see that call function has a value of 111. And then duptop has 64. Before it was 131 and 4. So it's interesting that the Druva opcodes have a different instruction to opcode mapping. So I told you we talk about code objects a little bit more. So again, here's that graphic. The code object follows the magic string and the timestamp. And this piece is very important because the code object contains all of the instructions. It contains the opcodes and the operands for each instruction. That code object can also be executed. So inside that PYC, if we were to read, starting at byte index 8, like we saw, we could read the code object using the Marshall module. We can load those code bytes into a code object. And if we were to execute the code object, we get the expected output, hello world. So inside that code object, like I said, that's where the instructions are. And there is a field called code, which has all of the raw bytecode. So like D, for instance, actually represents an integer value that is an opcode. And then there are operands in here as well, which we'll see. So like I said, the idea was that I wanted to decompile the Druva inSync modules. I wanted to be able to see their source code. But before you can, so an intermediate step prior to being able to decompile something is disassembling it. And the dis module allows you to disassemble a code object. So with our example, the hello world, we could see that just printing out hello world results in quite a few instructions. First, we load up the hello world string constant, which is stored in the constants tuple at index 0. That item is printed, then there's a new line printed, and finally we return a value of none. Okay, so that was a simple hello world example. In the real world, applications are way more complex than that. You're not going to run into many hello worlds. You're going to run into object-oriented types of programs with classes and methods and whatnot. So here's another example. This is my hello class. You can see that there is a constructor. It doesn't do anything. And there's a method that just says, oh, hey. So again, this is a very simple example. However, it makes code objects much more complex. So if we were to disassemble this code object, the one instruction I want to point out to you is this load const, because it loads a code object out of that constants tuple. And if we were to look at that constants tuple, we would see at index 1 that there is indeed that code object. Now, if we disassemble the code object that's in the constants tuple, so index 1 here, check out the lines I've pointed to. There are even more code objects being loaded. So as you might imagine, these code objects get pretty complex when you have, very complex classes and stuff. So my next step was, knowing all of this, how do I fix the opcodes? And the approach I took was to remap the opcodes. So since we had the opcode map for Druva, and we have an opcode map for a normal Python 2.7, we could disassemble the code objects found in the Druva PYCs. And you would go through that raw bytecode, look for opcodes. When you find an opcode, check the map. So 111 maps up to call function. And then we also know that the correct Python 2.7 opcode is 131. So we would replace 111 with 131. And then so on for each instruction. If we find a 64, we know it's a dupe top, we'll replace it with 4. So that's how you go about fixing the opcodes. Now, it's a little bit more complicated than that because of those nested code objects. So we're going to work through this diagram real quick. So we want to decompile a protected PYC file. So that's our input, a PYC file. We know it has a magic string. It has a timestamp, and then it has that code object that we're interested in. So we pull the code object out of the PYC file, and then it gets sent as an argument to a routine that fixes code objects. This is where all the magic happens. So when that code object comes in, the code field is fixed. So that gets scanned for opcodes, and those opcodes get remapped. And we know that code consts, the tuple, can contain more code objects. So the next step is to loop over that tuple, look for code objects. If there are any more, then we would send them through this routine again. And that's where the recursive nature comes in. So the output of this function ends up being a new code object. Code would be remapped, and the constants tuple would contain more code objects that get remapped as well. And this results in a brand new PYC file. And in order to make it work with uncompile 6, you need to set a documented magic number. It doesn't matter what the timestamp is, but like if we did it today, we would set it as March 27, 2021. And then we push that brand new code object in here. And unfortunately, I can't show you the Druva source code because it's, it's intellectual property. So we've seen how a PYC file can be remapped, and that's a static file, right? So this next protection we'll look at is SourceGuardian. We'll be looking at a runtime solution. So when I opened up Nagios XI, it had a lot of PHP code, and a large chunk of it looked very similar to this. So if you look at the top here, you'll notice first a function is checked for existence, and that's the SG load function. And if you kind of creep down here to the bottom, you'll see that SG load gets called, and the argument to it is this big blob of characters of data. Now, this represents an encoded file. For any PHP file that gets encoded by SourceGuardian, it'll end up looking like this, except this argument will be different. What I like to call this is the SourceGuardian wrapper. When you run an encoded file and execute it, the file knows how to decode itself and execute itself. And all of the decoding magic takes place in SG load. So I'll take a quote off of the SourceGuardian website. They say that our PHP encoder protects your PHP code by compiling the PHP source code into a binary bytecode format, which is then supplemented with an encryption layer. So they compile your source code and then encrypt it. So SG load decrypts and then executes the bytecode. Okay, so we'll take a little quick glance at some PHP internals here. So PHP bytecode, it's similar to Python bytecode. However, I don't know of a concept of a PYC file, that static, compiled Python file. However, there are PHP extensions that precompile scripts. And one that you might recognize is Opcache. Opcache improves PHP performance by storing precompiled script bytecode in shared memory, thereby removing the need for PHP to load and parse scripts on each request. Now, it serves the same function as a PYC file. It's there to make load time much faster. Now, in general, even if it's not cached like this, PHP code will be compiled into bytecode, which is executed by the ZenVM runtime. So PHP and the Zen engine also provide hooks for extensions that can allow developers to control the PHP runtime in ways that are not available from PHP userland. Some hooks that we'll see moving forward here are ZenCompile file. That is the hook when PHP code is compiled into bytecode. ZenExecute is there when the bytecode gets executed by the VM. And also we'll see some opcode handlers being overwritten. And an opcode handler is just a C function that is designed to handle a specific instruction. So for instance, if an echo instruction were encountered, it would know to print a standard output. Also, various PHP functions can be overwritten and hooked, like variable dump. So hooking is a very useful process for debuggers. I'm sure if you've ever debugged code, you'll set breakpoints on various functions. You want to stop execution when that function gets hit. That is an example of hooking a specific function and overriding it. So next we'll look at the Vulcan logic dumper extension. And this is an extension I made heavy use of in order to decode this SourceGuardian at runtime. But the way it works is, so we'll start with this example, but we have a hello world. If you were to run Vulcan logic dumper on an unencoded PHP file, it would show you the instructions that are compiled. So this compiles into bytecode, and this is a representation of the bytecode. We can see that it executed properly. But again, you have two instructions, an echo and a return. So VLD hooks at compile time. So at the point when source code is compiled into bytecode, that's where VLD out of the box will do its hooking. And I've showed you a little snippet here of what the extension looks like inside of the compilation routine. So first, the original Zend compile file is called. It converts it into bytecode, which is represented in an op array. And then there's a function called to dump the op array. So this is the output of that VLD dump op array. Now, if you were to run VLD against a SourceGuardian protected file, you wouldn't get the output that you're interested in. The reason for that is because we're hooking at compile time. Now, a SourceGuardian protected file contains all of the code necessary to decode, so really to decrypt and then execute the compiled, the protected bytecode. The problem here is that if we're hooking at compile time, the only instructions that we're going to dump are the wrapper instructions. So as you can see, we check for existence of SG load. And further down, what you can't see is where SG load gets called. But we're interested in the argument to SG load, not this wrapper code that tells it to decode the protected bytecode. So just to give you an idea of kind of what happens here with the hooks, when a SourceGuardian protected file is launched by the PHP interpreter, all of that wrapper code is compiled into bytecode. So that wrapper code gets turned into an op array. That includes the call to SG load. And then all of that compiled wrapper code gets executed. So this in turn calls SG load. SG load fires, and it decrypts it decrypts the encrypted bytecode and calls Zend execute to execute that decrypted bytecode. So you can see that there are two calls to Zend execute here. We're executing two sets of bytecode. We're interested in the second hook of Zend execute because that is when the decrypted bytecode is executed. Okay, so from here, I modified the Vulcan logic dumper extension to instead try to dump opcodes when Zend execute fires versus Zend compile file like we saw before. And I set it to dump on the second invocation of Zend execute. Now here is my function that fires when the hook is caught. First, I print out execute, and then I call VLD dump op array, and then I'll actually execute that op array. So with the hello world example, you can see that execute was called. It clearly executed fine because we got the output we expected, but no instructions were dumped. So I had to figure out why, and the way I went about doing that was by debugging the PHP process. So I debugged running that hello world SourceGuardian protected file. And I set breakpoints on Zen to execute. Like we talked about, we are interested in the second invocation of Zen execute. So here we go, we hit the breakpoint. And here I print out the op array. Notice that the line start is 0 and the line end is 0. And interestingly enough, if you were to look at all of the instructions, they all have a line number of 0, which is kind of strange. And each of these little outputs here represents a Zen to op structure. A Zen to op has a handler, it has operands, a line number, opcode. So this represents an instruction. So that VLD dump op array function ends up calling a VLD dump op function that will dump out an individual instruction. And when I looked at that source code, because I'm trying to figure out why are no instructions being dumped, I saw this little if block down here. If the line number is 0, then an instruction would not get dumped. So I ended up commenting that out, and sure enough, I got some output. So the top up here represents the hello world, that is, I SourceGuardian protected it. And below is sort of the expected output that we're aiming for. This is this was dumped with an unprotected hello world using VLD. So if you look at the differences here, the protected file has an additional operation, and it's this jump that's prepended at the beginning here. Also, what's weird is if you were to jump and follow the jump, it takes you to instruction 2. So if you were to execute all these instructions, it would just jump and return. There would be no echo, which clearly isn't the case. So I needed to dive in a little bit deeper here. I started with this sample. We generate a random number, either 0 or 1, depending on the output, or depending on the random number, we'll either output a 1 or a 0. So it's pretty simple. When I encoded that and ran it through my VLD, I got some similar kind of output that we did before. So again, this is the expected. This is an unencoded sample. This is an encoded sample. So again, we got additional instructions, 12 versus 10. We got that prepended jump. And similarly to the hello world, if you were to follow that jump, it takes you straight to operation 4, which is a sendVal1. And then beneath that, you have a do function call, random. So if you were to follow this logic, it takes you to the random call, but only 1 is sent as an argument. 0 is never added as an argument. So this doesn't match up to this down here. We have a sendVal0, sendVal1, do function call rand. Additionally, if you notice, there's a jump Z and Z. Down here, that instruction doesn't even exist. There's just a jump Z. So clearly we have some weird stuff going on. If we go back to the debugger, and this is the hello world, remember that there were 3 instructions. There was a jump, an echo, and a return. And I talked about that handler. Zendop has an opcode handler. If you were to look at the handlers here, the jump handler function does not have a symbol associated with it like the other 2. So echo has a symbol associated with it. It clearly looks like it's some sort of Zend engine function. And return also has a Zend symbol associated with it. So that's kind of strange, right? Now, I checked out the loaded libraries and the addresses, and that jump handler address actually fits in the range of the addresses for the SourceGuardian loader extension. And that's what this funky file name is. That's the SourceGuardian extension. I set a breakpoint on that. And when the jump handler fired, it confirmed what I just saw, that that jump handler exists inside the SourceGuardian loader extension. Now, if we were to enter that SourceGuardian jump handler function, something that stood out to me was a specific call instruction, and it calls a function pointer. When I stepped into that function there, it ended up calling the Zen jump handler. So the SourceGuardian jump handler does a whole bunch of stuff, and then it ends up calling the Zen jump handler, which is kind of strange. So if you were to take a look at the jump instruction prior to entering the SourceGuardian jump handler, and then compare the instruction to right before the Zen jump handler is called inside the SourceGuardian jump handler, you would see that operand 1 actually changes. And since it's a jump, operand 1 is a jump address. Basically what that means is before the Zen jump handler handled the jump instruction, the address changed, which means that the jump would have gone to a different instruction than what we saw in that output. And to kind of recap on that, here's the SourceGuardian jump handler. So when that function is fired, the current operation, which in this case was a jump, is referenced, and then the operands, which is the jump address, are deobfuscated. Then the Zen VM's jump handler is called with the valid operand, the valid jump address. And then prior to exiting that SourceGuardian jump handler, the operands were obfuscated yet again. So now we'll start to get into the solution. So the solution is that you have to fix each operation that's obfuscated. And what I did was, like for example, for the jump, I created a function and I based it off of that SourceGuardian jump handler function. So basically I copied all of that logic and I modified it a little bit. And what I did was I allowed the deobfuscation to occur, but instead of allowing the jump handler to fire, I set the instruction handler, that jump instruction handler, to just point to the Zen jump handler. And then I didn't allow the operands to re-obfuscate. So in essence, I'm fixing that jump instruction. Now, that's just fixing the jump instruction, but there's an entire op array that needs to be fixed. So before, if you remember, when we dumped an op array, we'd be dumping obfuscated values. And then when those instructions are executed by Zen execute, the operands are deobfuscated, the Zen handler executes it, so then instruction fires, and then the operands are obfuscated again. So my solution was to fix the op array, dump the op array, and then execute it. So when I fixed it, like I said, I modified the SourceGuardian handlers. I allowed the instructions to deobfuscate the operands. And then I set on the instruction the handler to the Zen handler. When I dumped the op array, it was dumping the fixed instructions. And when Zen execute fired, the operands were fixed and the handler was the correct one. So in addition to the jump handler, there are several other instructions that were being obfuscated. And as you can see, like a lot of them have control flow implications. So we've got jumps, we've got go-tos, we've got conditional jumps, try catch. So there were 5 different SourceGuardian opcode handlers for these groups of instruction types. So I ended up having to create 5 different modified opcode handlers, and they followed the same logic. Let the operands deobfuscate, set the handler to the proper handler, and then don't allow them to reobfuscate. And here's a snippet of my code in the VLD extension. So right here, I would loop through the op array, look at each individual instruction. If the opcode ended up being a jump or a go-to, then there's a specific fixer function that I would fire. And again, in this switch statement, if it's 46, 47, 152, or 158, then I run another routine, and so on. So like we saw before with Python, classes introduce another layer of complexity. So I'll start with an example real quick. We've got class 1 and class 2. Each one has a func1 or func2, which echoes 1 or 2. Each of them, the classes also has a function that will not be called, and that they're called not used 1 or not used 2, and return value 1 or 2. So in the main function, or the main logic of the PHP script, I generate a random number 1 or 2 that will determine which class is instantiated, and then in turn, which function is called. Now, when I ran VLD against that, here's output of kind of that main logic. We can see that a random number is generated. Depending on that, either class 1 or class 2 is instantiated, and func1 or func2 would be called. Now, in this case, func1 was called and class 1 was instantiated. So you can see the disassembly of func1, and the output shows that 1 was the random number generated. Now, what I found was that in the output, it didn't dump the unused functions, and it didn't dump the unused class, which was class 2. So there was one more step I had to take in order to fully dump out a SourceGuardian protected file and all of its opcodes. So what we've been doing is dumping kind of the main. However, there's another piece that I had to tap into, which is the class table and also the function table. And these define entries. So in this case, there was a class 1 in the class table and a class 2 along with their function entries. However, we didn't have just a static function defined in the file, so I didn't have to tap into that for this particular example. But basically, we fixed that op array, we fixed the op arrays in the class table, fixed the op arrays in the function table, and then we could dump it. So after I tapped into the class table, function table, my modified VLD would then dump unused functions and unused classes. So as you can see, the not used one was dumped here, along with func1. And also, you can see that class 2 in its entirety was dumped. We can see func2, not used 2. So thank you all very much for joining. Just to recap, we talked about remapping Python opcodes in a static PYC file. And we also talked about fixing PHP bytecode at runtime. I hope, if you ever run into something like this down the road, that this is a good reference for you to refer back to, and hopefully you have a leg up. If you're interested in diving a bit deeper, I've written a couple blogs. It's on the Tenable Tech blog. And also, I've dumped all of my code for Python Opcode remapping and SourceGuardian decoder extension. And at this point, I'll open it up for questions. Food lecture. Oh, thank you. Does anyone have any questions?
Up here all alone. I'm not. If your room monitor, she may have been having trouble with her mic. And I don't see any questions in the Q&A, but we can go back to floor and everybody can, and maybe you can hang out at the tables for a little while. And if anybody has any questions, they can come and ask you. It was a great talk though. Thank you.
Oh, thank you very much. Yeah, thanks all for joining, and thanks to BSides Tampa for having me.